So the second presentation is about new analytical solutions for gravity change modeling. And in this case, we are considering triaxial deformation sources that I will explain how they look like and what we consider as a triaxial source. So this work, yeah, we developed everything together. I mean, Eleonora and me, and the outline of the work is as you see here. The motivation is inferring the location of magma intrusions and tracking them. And we wanted to have analytical solutions for this purpose, analytical solutions for both deformation and gravity changes. Analytical solutions can be used for inversions, almost in real time, and therefore they can be very, very useful in this sense. This way, we will be able to perform coupled inversions of surface displacements and gravity changes, and this way we can use this data in a much better way. They provide us more information, as I will show you later. And we have also developed an adaptive solution for finite ellipsoidal sources, because these solutions, as you will see later, first we developed solutions for point sources, but you will see that we also have different solutions for finite ellipsoidal sources. And in the end, I show the perspective for mechanical imaging of volcanic plumbing system and summarize the presentation. So magma intrusions in general have complex shapes. In most cases, we don't know the real shape and location of magma intrusions. Sometimes the magma intrusions sometimes just accumulate in a magma chamber, pre-existing magma chamber, and sometimes they make their way all the way to the surface. And in these cases, we have eruptions similar to fissure eruptions that we see from time to time also at Etna. As I showed you in the previous presentation, if we have a gravimeter, then we can measure the gravity change due to the intrusion. And in this case, we simply use the Newton's equation, as all of you are familiar with. So another important point that was already raised is the deformation effects or the deformation-induced gravity changes. Once we have magma intrusion in a magma chamber, in the medium in general, we have uplift, we have surface deformation in general, and therefore we will have the well-known free air effect for the gravimeter and other effects. Like another important effect is the density change in the host rock in the medium, as represented by this darker gray color here. So while we can observe the vertical displacements on the surface using GPS or leveling and this kind of geodetic techniques, the density change, the subsurface density change, can be estimated only using models. It is not possible to observe directly this quantity. So one way to do the modeling is to assume some sort of an idealized shape for the magma intrusions, and then for this idealized shape we can calculate the strain and the displacements on the surface, and therefore we can also calculate the density change in the medium and the resulting gravity change due to that. So I'm summarizing these different contributions in this figure. The dashed line that you see here show the walls of a magma chamber before the intrusion, and after some magma is intruded into this magma chamber, the walls are pushed to this big ellipse that you can see here. And this white area that we have in the middle between the new chamber walls and the existing magma in the chamber, this is the magma that was in the chamber before the intrusion took place. This volume is available for the magma, for the new magma to reside in the chamber. So these two changes due to the intrusion they have their own gravity signal. So the first contribution that we have on the surface is the contribution from the formation of the new cavity due to the pressure increase. And the second one is the mass of the intrusion, which is placed within this available volume. Then we have the host rock density change. As you see with these dark and light gray areas and these contour lines, we have density changes that depend on the shape of the source, by the way. If the source shape is different, or if the source is rotated, the pattern changes completely. So, but yeah, if we have the density change everywhere in the medium, we can calculate this component. The fourth component is the free air effect, which is the change due to the elevation change at the gravity station. And the last contribution is from the surface displaced mass. So the gravimeter at the beginning, before the chamber pressurization, was located here. Now it moved upward, and of course it is not hovering in space. There is new mass below the gravimeter, which is the displaced surface. This also contributes to the gravity change. And all in all, we can put all of these contributions together as in this equation. And you see that the gravity change that we measure is the sum of all of these contributions. And in order to constrain this intrusion mass, we need to deal with all of these other terms first. And this is the main task we had in mind. So for some simple source geometries, like a spherical source, Hagiwara 1977 and Walsh and Rice 1979, they showed that for spherical sources, the sum of these three terms, like delta GSM, delta GHD, and delta V, is 0. Basically, he showed that the main contributions are, the only contributions are the intrusion mass and the free air effect. So very simple in this case. For a more complex case, which is for dislocations, for rectangular dislocations and point dislocations, Okubo 1991 and 1992 derived exact expressions using which you can calculate all of these terms. So we have this analytical solution for that case, but for triaxial sources, like what you see here, we don't have any analytical solutions. Therefore, we did this work that you see here. But what are the triaxial deformation sources? Yeah, as I mentioned earlier, you can think of them as a magma chamber, sometimes as a lens filled with magma, pressurized when the new magma is injected inside. And in some cases, we have these pictures from petrological studies and other geophysical measurements, geochemistry, and all different volcano sciences. And we have a more complicated shape for the magmatic system of a volcano. So in general, by a deformation source, by triaxial deformation source, we consider any kind of general deformation along the principal axis of source area. The source area can be the lens together with other lenses and a part of the mush that we have below the volcanoes. And then these deformations can be completely different. They don't have to be uniform in all directions. So this is what we consider as a triaxial deformation source. In some cases, we assume an ellipsoidal shape, and in some other cases, we just refer to the different strain in different direction as our source. Bonafede and Ferrari 2009, they showed that a spherical source of pressure can also be represented as three mutually orthogonal tensile dislocations, as in this configuration you see here. As a part of my PhD work, I extended this solution to a new solution, which is called the compound dislocation model, or the CDM. And in this case, we have three mutually orthogonal rectangular dislocations that can be different, that can have different size and can be oriented arbitrarily in this space. They can take any arbitrary orientation in this space. Also, I developed this point source version of the source, which is in which I replaced the finite dislocations with point tensile dislocations. And this source can represent general triaxial deformations in a half space, elastic half space. But why this point CDM can simulate volumetric sources? Here I'm showing two different volumetric sources. One is an ellipsoidal source in cross-section, of course, and the other one is a cuboidal source. So these sources can be represented as a number of dislocations, like different forces acting on the walls of these sources. If you are far enough from these sources, then one can assume that all of these sources, all of these dislocations and these forces are concentrated at the center of the source. And if we superimpose all of these sources there, then the result would be a point CDM. So this can be shown mathematically. Therefore, the point CDM can represent different kinds of volumetric sources of pressure. And it does not assume any specific shape in the beginning. Based on, so this is basically the story about one point CDM, and we know that a point CDM represents different kinds of volumetric sources in the far field, meaning that if the source is deep enough. But in the near field, the finite dimension of the source needs to be accounted for. As shown by HLB 1957 and also Yang et al. 1988, a solution can be formed as an evenly spaced distribution of point sources within the finite source, in the case that the source is very shallow. So in other words, if we have a distribution of point CDMs similar to this configuration that you see here, we also have the solution for the near field. However, this way the computations might be very time consuming, because we need to have many of these points. But we can use this for validation purposes, as you will see later. Before that, I compared this point CDM with ellipsoidal sources of pressure. For this purpose, I considered the moment tensors of the point CDM and also of pressurized ellipsoidal sources. These diagonal elements of this moment tensor, they basically reflect these different forces that act that form the point CDM. We have the similar ones for an ellipsoidal source of pressure that can be calculated based on HLB's theory. So in order to compare these two solutions, we can compare these moment tensors. Here, M1, M2, M3 represent the eigenvalues of this moment tensor. M1 is the maximum and M3 is the minimum. If we consider this figure, on the horizontal axis, we have the ratio of the intermediate to maximum eigenvalue, and on the vertical, we have the ratio of the minimum to maximum. So for all possible sources, for all possible ellipsoidal sources of different aspect ratio, we can find a point on this plot. And for all possible CDMs, for all possible aspect ratio for the CDM, we can also find a point on this plot. And as you can see, all the possible places for ellipsoids form this dark gray area, and for the CDM, we have this area. It means that the ellipsoids are a subset of the CDM. In other words, the CDM can represent the ellipsoids of all different aspect ratio, like spherical, all the oblate ellipsoidal sources, as you can see on the diagonal of this plot, crack-like sources, and spheroidal and general triaxial sources, and cigar-shaped ellipsoids. But also, we can see that the CDM can represent some other sources that cannot be represented as a pressurized ellipsoid. An example would be open vents, open conduits. So now the analytical solution for gravity changes. So far I talked about the deformation, the solution for the deformation, but for the gravity change, we use the same configuration of the tensile dislocations in the point CDM, and we used Okubo 1991 solution for point dislocations. Using this solution in this configuration, we could develop this analytical solution for gravity changes. So this is the general solution for deformation and gravity changes associated with a point triaxial source. So the paper is already under review in GRL. So in the same way that we could form, we could make a solution for the near field for finite sources. We can also follow the same procedure to have the solution for the gravity changes associated with such a source. So the theory is completely the same. I just wanted to mention this, don't say anything more. And then we have the benchmarking. In this case, we used the finite element solution for the gravity changes after Terzatti and Bonafede 2008. So they used a spheroidal source like this one, located at 5 kilometers below the surface. And this was a source of expansion without any added mass. Basically, we don't have this fluid mass in the equation that I showed you earlier. So for this case, the Terzatti and Bonafede calculated the surface displacements and the gravity changes. So here I calculated all of these components using the point CDM and a configuration composed of n point CDMs to see whether there are any near field effects. So you see the black line, the point CDM is very, very similar to the numerical solution, which is the green one, but the endpoint CDM does a better job in the near field. But in the considering the gravity changes, we see even a better match. These plots are normalized by these curves. All of them are normalized by the delta G SM, which was the surface mass contribution. So you can see that the host rock deformation for this particular aspect ratio is almost 60% of this contribution. So this is very significant, and contrary to the point that some believe that these deformation effects are negligible, actually they are not, and you can see other source geometries with even higher values for this host rock contribution. And the volume change as well, the contribution of the volume change is also very large, but the total gravity change that we observe is the sum of all these three, and you see that it is basically again reflecting that the sum of these terms is significantly different from zero. So the shape of the magma chambers and the deformation sources are very important to be considered in the gravity change model. So to show this in a different way, I considered three different sources of different shape. One is a spheroidal, one is spherical, the other one is a horizontal crack-like source. As shown by Dietrich and Decker 1975, we can change the source depths such that in the end we get similar vertical displacements for these three sources. But if we look into the radial displacements, we see that the patterns are completely different. The conclusion is that in order to constrain the source depth and shape properly, one needs to use the vertical displacement and the radial displacements, both of them. Based on vertical alone, we cannot do a good job. So for these different sources, we also calculated the gravity changes. And as you see, that the patterns are completely distinct. This means that the gravity changes also reflect some information on the source shape and all the deformation source parameters in general. These sources, in this case, we assume that all of them are massless, but you see that the deformation effects are already causing these distinct patterns. Similarly, we considered, we changed the source depths such that in this case we get the same radial displacements, but as expected, the vertical displacements were completely different, and the gravity changes were also completely different, confirming the same point as in the previous slide. This is also a part of a manuscript of the manuscript that is under review in GRL. And by the way, the preprint of that manuscript is already online, just in case you wanted to take a look. So to summarize this part, the coupled inversions of displacements and gravity change can be very important, because gravity changes contain information on both the mass change and the deformation source parameters. And this way, if we use the gravity changes in the coupled inversions, we can better constrain all source parameters, not only the mass change. And another implication is that using the gravity changes in coupled inversions, we can use either vertical or horizontal displacements along with the gravity data to fully recover the source parameters. This is an interesting result with some implications that I point to one of them here with this synthetic test. Here I consider an oblate source, which is this circle here. Here we have the top view and the cross section. As you can see, the source is located at 2 kilometers below the surface, and the semi-axis are 1 kilometer and 300 meters. So for these three stations, I calculated the surface displacements and gravity changes caused by this source of expansion. So after calculating the displacements, I added some noise, some synthetic noise. So in this case, I considered the noise on the vertical displacements is 3 times larger than the horizontal components, and the noise for the gravity signal is 2 microvolts. Then I used the synthetic data in an inversion to constrain the volume change and the mass change associated with this source. And in the first case, I used the synthetic vertical displacement to calculate the free air effect and remove it from the gravity signal. And then I inverted the gravity data. In this case, I have done the inversions separately, separate inversion for displacements and a separate one for the gravity changes. But if I do the joint inversion after removing the free air effect, we get some results which are similar to this first case. So something is not working according to what we expected. And the fact is that if we do not correct for the free air effect and run the joint inversion, then we can also exploit the gravity data for the information they have on the vertical displacements. And in this case, we can see that we can constrain all of these unknowns in a better way. In one case, in this green case, we have used all of the data. For the blue case, we have used only the horizontal displacements and gravity changes, no vertical displacements. And the last one, we used only the vertical and gravity changes. And in all cases, you see that they constrain the mass change much better than the other case. And this is just one slide showing the new solution that we have developed for finite ellipsoidal sources. This is an adaptive solution that basically is depth dependent. The distribution of the point CDMs within the source is depth dependent. This way we can represent a finite source with a lesser number of point sources and can calculate the surface displacement very, very quickly. Here you see how the source distribution is a function of the depth. The closer to the surface, the more sources we need to have, the more point CDMs we need to have within the ellipsoid. But in all cases, we get a very good agreement with other analytical solutions. They are identical. In this case, I compared the solution with Yang solution, and the calculations corresponding to this source can be done in a fraction of a second mostly. So this solution is perfect for inversions, and this is a solution for triaxial sources, by the way. So can be very useful for that purpose. In perspective, we consider the mechanical imaging of volcanic plumbing system. Basically, what we want to say is that this solution for deformation and gravity changes can be applied to mechanical imaging and eruption forecasting. So here I show the results from Boudoussel et al. 2020 for Piton de la Fournaise. They consider the GPS data, GPS time series, as you can see in this plot, these baselines represented here. And using the point CDM, only the deformation solution, they were able to perform unsupervised real-time inversions. And by doing so, they could track the magma intrusions through time. So you see the color bar shows the time. So these blue sources were there earlier than the other ones. And you see that the color shows the evolution of the intrusion in the system. So this was this is very, very interesting, but just imagine that if we use the gravity changes together with deformation data, we can also constrain and we can get some information on the mass change associated with these intrusions, which is a much more powerful tool for eruption forecasting. Yeah, in summary, basically, these are points that I already talked about, so I leave them here and I'll take the time for questions. Thank you.
Questions for Mehdi? A lot of applause.
Thank you. I hope this addressed the question, the previous question from Vincent. So
yep, no, it's very interesting to see the modeling you're doing and what you're expecting in terms of data and different signals from different sources. So
thank you.
Very interesting.
Thank you.
More questions? We have time for a couple of questions before the coffee break. Okay, if
I also should appreciate very nice comments and support from Daniela and Flavio. I forgot to mention it in the beginning, so I take the time to thank them again. So we are going to get back to them for this other finite solution as well. So.
Okay, we have one question from Gary Barnes.
Thank you for a very interesting couple of presentations there. One thing that sprang to my mind, thinking about an array of gravimeters and looking at mass changes, was Gauss's flux law for gravity changes. That might help in distinguishing between the mass changes and the other changes. Is that something that applies here? Is it something that you considered?
You mean basically gas flux as the causing the deformation and the gravity change in general, right?
Oh, no, sorry, Gauss's flux law, as in the integral of the gravity over a surface is equal to the change in mass.
Gauss.
Gauss. Okay. Sorry. Excuse me. Yeah. Right. Cannot be the case for all different cases, because we have the compressibility of rocks, right? So the volume change that we have within a magma chamber, within a source, within a deformation source, can be different kind of sources. Does not necessarily have to be a magma chamber. It is more complicated than what I showed here. So we have, in other words, we have the compressibility of the host rocks, and at the same time we have the compressibility of the material within these deformation sources. And considering that, considering the fact that the magmas can be very, very compressible, right? Then the mass that we expect in these different sources sometimes can be completely different from what we have at the surface. In some cases, for example, you see at Etna, we have this gravity change signal, but not very large deformation signal. So even in such cases, we might have a lot of mass coming into the magma chambers, but since they are compressible, we don't get much of deformation. Therefore, the area integral, like using the Gauss theorem, as you mentioned, is not going to tell us anything about this mass, intrusion mass in that case. And in some other cases, we also have literally, we have gases that are injected into magma chambers, or we have degassing within a magma chamber. So we have literally no mass, no intrusion mass, but still we get the deformation on the surface. So therefore, this mass at the surface cannot be reflecting any intrusion mass. I hope this answers the.
Yes, very, very, very good. Thank you very much.